Hi there, and this is an organic lesson for organic multiple choice. And today we're looking at the March 2022 paper. And we'll be looking at questions 26, hopefully to 40 if we're quick. All right, and this is the organic part. This is the organic chemistry part of the multiple choice. In the old days, it used to start at question 20, but now they're going to start at around 26, okay? Because we don't have those weird options at the end anymore. All right, in this question, alkenes, cyclic alkenes should be considered. Alkenes and cyclic alkanes should be considered. How many structural isomers are there of C4H8? Oh my word, that's a hard one. Now, let's have a look. One, two, three, four. That's one structure you can get with four. One, two, three, four. That's another structure you can get with four. And one, two, three, four. Because it says you should consider cyclic alkanes as well. Okay, so there, believe it or not, with four carbons, they're the only four structures you can get. Now, obviously, this one, well, I hope it's obvious to you guys, but this one is going to be an alkene. This one is an alkene. But because we bend around in a circle, this one's going to be an alkane. Okay, so this one, H, this is C4H8, which is the one we've got to do. All right, where are we? C4H8, there you go. So this is the only alkane. It's the only one. All right, there's no other ones. Now, the other two, all right, now obviously at the moment we have three isomers. Okay, and now what we've got to do with the other two is change the position of the double bond. So the double bond could be here, and this straight one, that makes four isomers. Or, where are we? Where's my pen? Or it could be in the middle here. That makes five isomers. Now in this one here, the double bond could be here, or here, or here. But they're all the same position. Does that make sense? So believe it or not, there's only one isomer with the shape of an alkene, okay, like that. But there's two of these. So in total, the answer is five isomers. Anyone want to argue with me? Five isomers there. Are we good? Manolo, you good? Anyone else are good? Abote, you all right? You can just type. Yeah, Manolo. Yeah, that's not an easy question actually, but the answer is five. And the only way you can do it is you've got to draw them, and you've got to do a million of these. Eh? Which compound will decolorize bromine? Now, to decolorize bromine, we're looking for a carbon-carbon double bond. I'm looking through the first structure, and that does not have one. I'm looking through the second structure, and that doesn't have a double bond. The third structure, well, let's have a look at D first of all. D doesn't have one, but structure C does have a double bond. I don't know if you can see it here. Okay, the only way you can get CH and CH is if there's a double bond there. Does that make sense? So the answer must be C there. Any questions there, guys? Please feel free to ask. Okay, there's not many of us today. All right, are we good there? Anyone say anything? I don't mind. Okay, I'll go on to the next one. Okay, and this is 28 and 29. Let's have a look here and paste these. All right, there we go. Now, where have you guys gone? All right, well done. Alkenes react with aqueous hydrogen bromide. The reaction proceeds via an intermediate carbocation. The more stable the intermediate, the faster the reaction. We know that, don't we? So before I do anything else, this is about the stability of carbocations. Okay, that's the topic we kind of got to think about here. All right, which sequence correctly shows an increase in the speed of reaction of the alkenes with hydrogen bromide? Now, in other words, we want the slowest on the left, and then all the way up to the fastest. Now it says here the reaction proceeds via an intermediate carbocation. The more stable, the faster. Now let's have a look at the first three: ethene, propene, and 2-methylpropane. Ethene looks like this. Again, this is quite a hard question. Propane looks like this. Okay, there's propane. And what's the other one? 2-methylpropane looks like this. It's a methyl there. Then it has a methyl here. I'm just going to write CH3. And then that. That's 2-methylpropane. Now, there are the three. All right. Now, which one is, well, let's have a look at the intermediates. Now, unfortunately, guys, you just got to do a lot of these. If you do this, let me get rid of the double bond. The double bond is going to go there. The double bond is going to go there. And the double bond is going to go there. Where is the positive charge going to go? Well, the hydrogen that adds from HBr is going to go onto the carbon with already the most hydrogens. So there's the hydrogen's going to go on there. In this case, the hydrogen's going to go on there. And in this case, where are we? The hydrogen is going to go on there. Okay? If the hydrogen goes on there, the charge must go on the other one. Okay, not an easy question. So which one is the most stable carbocation? Well, this is the most stable because it's a tertiary carbocation. This one is a secondary carbocation, and this is just a primary carbocation. So believe it or not, the slowest is going to be the primary, then the secondary, then the tertiary. So amazingly, we have the right order already. So the answer is A there. Are there any questions there? That is not an easy question at all.
Sir,
Oh, yeah, go for it. Who's
please
that?
explain all of that because I'm lost.
All right, dear, don't worry. All right, then. So now there's, you know what, dear, body man, there's a lot going on with this question. All right, it makes me realize how horrible organic chemistry is. All right, seriously. So let's toss this aside like that, and let's have a look at the mechanism. Now, why is there a lot in this question? Because you just can't answer it straight off. So you have ethene. There's ethene. Okay, and now what you have to know is HBr is going to attack ethene. Now, as you know from Markovnikov's rule, the hydrogen will attach itself to the carbon with the most hydrogens already. So what's that going to look like? Well, they're both the same in this case, so it doesn't matter where the hydrogen goes. So let's say the hydrogen goes there, the one that adds on anyway. And if the hydrogen goes there, it means the other carbon gets the positive charge. And this is the intermediate, which the question is talking about. Okay? And as you can see, the intermediate is what's known as a primary. It's a primary carbocation. Okay, there's the first one. Okay, so let's do the second one. The second one was propane. Okay, so this is propane. Now, yeah, but you know what, dear? I know what you mean. This is a hard question, seriously. There's propane. That's why organic is so hard, There's the HBr coming up. And which carbon is the hydrogen going to attach to? It could attach to this one or this one. But it's going to attach to the one on the right. It's going to attach to this one because it already has two hydrogens on. All right? That's Markovnikov's rule. So the intermediate here will look like this. Okay? So, oops, Kettler was here. Okay, so where are we there? So this is, oh God, everything's making noise now. There's the hydrogen that's added. Oh, go away. Why have you gone? There it is. There's the hydrogen that's added, and that means this carbon gets the positive charge. Okay, now,
Wait, sir,
yes, dear, what's up?
you said, okay, like you said that the hydrogen attached to the carbon with the most hydrogens attached to it already.
Yeah.
Then why on earth is it attaching to like on the second the secondary carbocation? Why is it attaching to the either the second or the if you get what I mean?
I
Yeah.
think.
Why is it?
All right, relax, dear. I do. Let me turn my speaker down. Right out loud, dear. All right, now let's have a look. You're quite right. I think you're right. I think you understand what you're getting at anyway. So, which one of these two? Let's call this one number one, and this one number two. All right, buddy man. You can answer on the microphone if you want. How many hydrogens is attached to carbon number one?
One,
Exactly. And how many hydrogens is attached to carbon number two?
two.
And so, which one will this attach to?
Number two.
Yeah, and that's where I've shown it there.
Why is it attaching to that, like, that end chain? That's like one of the three hydrogens attached to it.
Well, because that one, darling, isn't part of the double bond, is it?
Oh.
Oh, body bar now. Can someone throw something at her? All right. So you're good with that now. It's got to whatever's going to attach to the double bond, to the alkene. It's got to attach across the double bond. Does that make sense?
Does. Thank
Yeah.
you.
So you only look at the ones that are across the double bond here. Okay. So it's going to attach to carbon number two, and that means therefore we get this carbocation, and this is known as a secondary carbocation. Okay? All right. Now, of these two, which carbocation is more stable? Would you think? Anyone? The secondary or the primary? You can type, guys. It's not just body burner. Which one is more stable, the secondary or the primary? Anyone, anyone can play. All right, no one's going to play. Fine. All right, I'll tell you. Yeah, well done, Manolo. It's the secondary. Okay, so already we have which one's going to be the fastest then? Well, according to the question, the secondary is going to be the fastest. Okay, so let's do the last one. And the last one, if you remember, is methylpropane. Okay, so let's draw. This is propane again. I'm going to draw propane first. There's propane. But now I'm going to take this hydrogen away and I'm going to put a methyl there. There's a methyl. Okay. Now, once again, I don't know where my color went. Once again, the HBr comes up to the double bond. Which one is it going to attach to? While I'm writing this. Now, let me call them numbers so you can guess. It's got to be this one, number one, or number two. Okay. Actually, I shouldn't number them one and two like that. I've just realised. Because, yeah, let's start again. This is number one and this is number two. Because this is the actual number one. This is the proper number one. Yeah, it's actually number one it's going to attach to. Why? Because number one has two hydrogens and number two doesn't have any hydrogens. Okay? So I'm going to draw the intermediate here. There's the intermediate. And it attaches to carbon number one now because I changed my mind, didn't I, about what it was called. So this is there. Now, if that's the case, then the positive charge must be there. And this is the carbocation. And in this case, this is a tertiary carbocation. Now, and you should all know this, primary carbocations are less stable than secondary carbocations, which are less stable than tertiary. Okay. Now you've got to know that we did that in class. All right, and you got to know it. I'm sorry, guys, but you got to know that. All right, it's Markovnikov's rule, and we explained it. All right, now going back to this page, the ethene gives us a primary, the propene gives us a secondary, and the methylpropane gives us a tertiary. Now, according to the question, it says, via an intermediate, the more stable the intermediate, the faster the reaction. So, which one's the more stable here? The more stable one is 2-methylpropane, and the least stable is ethene. So, the order is this. This is the slowest. Ethene is the slowest. Then propane. Then 2-methylpropane. Are we all good with that? Are we okay with that one? 28. Now, what number, Nola? Now, all of us, let's think about this. Have a look at 28. All right. Where would you go in a scale of 1 to 10? How hard is 28? 1 being easy, 10 being very, very hard. Where would you put this one? As for hardness. Number 1 is easy. 5, do you reckon? I think it's like a 9, or 8 or 9. Yeah, I think this is a hard one. But listen, guys, if you understand it, honestly, get it in your head, eh? Because if a similar one comes up, you'll be able to do it. All right. But you know what? Organic chemistry is like that. You can't just read the notes. You can't. You've just got to do millions of them. All right. That's the only way, I'm afraid. All right. I'll do as many as we can when we get back next week. But this is what we got to do, eh? You got to do loads of them. All right, let's go on then. So number 29. All right, Bernardo, what is it?
So I saw on this other past paper there was a question. It wasn't really. It's kind of related to this one, but it
Yeah.
was ClCl was yeah, it was Cl instead. It was chlorine instead, and for the whole process, it had two intermediates, and I wanted to ask, like they were asking for two intermediates, and I wanted to ask what the other one was because I was a bit confused.
You and me both, dear. I have no idea. Do you remember the year or anything? Was it a multiple choice?
Mm, no, not really, because I did it before mocks.
All right. Listen, dear. Try and find it, send it to me, and I'll do it. All right. But
Okay.
otherwise, I have no idea what you're talking about. I'm sorry. All right. But don't worry, we'll get to them all. All right. But you know what? I hope you're all working hard over these mocks, over this holiday. You should have had a bit of a break, but you've really got to start working now. These multiple choices are hard. They really are. All right, number 29 anyway. So a reaction occurs when a sample of 1-chloropropane is heated under reflux with sodium hydroxide dissolved in ethanol. Which row is correct? Now, first of all, you've just got to know your stuff. Where are we? Sodium hydroxide dissolved in ethanol. Now, in our course, we start off with a halogenoalkane, which this is what this is, and we react it with sodium hydroxide, and we react it with sodium hydroxide. Okay? Now, if we do one way, if we do one method, we end up with an alcohol. How do you spell alcohol? Alcohol. If we do it the other way, we end up with an alkene. Okay, ethene or whatever. Oh, I don't know why I wrote ethene now. It shouldn't have been that. It should have just been alkene. Okay. Now, this is 1-chloropropane is a halogenoalkane. All right. What conditions do we use sodium hydroxide to get the alcohol? And what conditions do we use the sodium hydroxide to get the alkene? Does anyone know? These are the only two things we use sodium hydroxide for with halogenoalkanes. One, you get the alcohol, and one, you get the alkene. But the conditions are different. Does anyone know what they are? What the top one? How do I get an alcohol? Ethanol for alkene. Well done. If you want to get the alcohol, the sodium hydroxide is aqueous. But if you want to get the alkene, the sodium hydroxide is dissolved in ethanol. Now, there's no way that you could have guessed that. You've just got to know it. Okay? Um, you can't work that out, and that's why organic is mean. Okay? You've just got to know. So the first one, the chlorine comes off in this one. Cl is off, the OH is on. And in the second one, what do? We remove HCl. Okay? All right, we remove HCl. So the first one, is the top one an elimination or a substitution? Number 1 and number 2. Is number 1 an elimination or a substitution reaction? Number 1. Anyone? Anyone can type. Yeah, well done, Bernard. Again, you're right. Look, one thing's come on, one thing's come off. So number 1 must be a substitution. Okay? But we're not talking about this one, are we? Because they say the sodium hydroxide is dissolved in ethanol. So the answer must be A or B. It's an elimination reaction, isn't it? Now, if we eliminate, we end up with an alkene. This is the alkene, so the answer must be B. Is that one okay? Do you all realise how horribly hard organic multiple choices are? Yeah, I don't know, Kato. I don't know if that means you're okay or you realise how hard they are, because they're hard. Okay? They really are hard. And I'm not joking. Yeah, I know they're horrible. They really are horrible. Seriously. I wish they weren't, but they are. Let's, let's have a look at this one. Oh, this looks like another bad one. But you never know, do you? All right, there we are. All right, the diagram shows the structures of 3 halogen alkanes. Okay, there you go. P, Q, and R can all be hydrolyzed. Does anyone know what we mean by hydrolyzed? How would you hydrolyze these? Does anyone know? What would you heat them up with to hydrolyze them? Anyone know? If you don't know, IDK is fine. All right, but let's have a look. All right, if you hydrolyze, believe it or not, we've just been talking about it. All right, to hydrolyze these, you heat them up with sodium hydroxide aqueous, and you get the alcohol. So if I do this one, this Br becomes an OH. If I do this one, this Br becomes an OH. And if I do this one, this Cl becomes an OH. So they all turn into alcohols. That's called hydrolysis, because the water takes part in the reaction. All right, so there you go. Which row is correct? Which one is the relative speed of hydrolysis? All right. Now, which one's going to be easier? Let's have a look. Q, which one? Relative speed of hydrolysis. Which one's going to be fastest here, do you think? Maybe it's this one. Is this one the answer? Is this one, Bonolo, is this the one you wanted to know about? It looks similar to what you were talking about. No, it's not that one. Okay, dear. All right. All right. So which one is the fastest here? Anyone know? Which reaction is the fastest? Right, yeah, it is Q. Now let's have a look. Let's have a look at both of them. Okay. This one, P, is a tertiary halogenoalkane, and Q is a primary. R is a primary as well. Okay. Primaries undergo SN2, and there is one step here in a primary. All right, SN2 is one step. Believe it or not, tertiaries undergo SN1, and in SN1 there are 2 steps. Now, again, if you don't know what these things mean, you've got to look up what SN2 and SN1 mean. Okay, so now which one are primaries? Q is a primary and R is a primary. So now we've got to figure out which one of Q and R is going to be fastest. P is going to be the slowest. Okay. Oh, it doesn't even ask for that, does it? Which one? So all we're looking at is Q and R. Sorry about that. I've messed you up a little bit. Q and R. Now, which one is going to be the faster one? Q or R? Does anyone know why Q is faster than R? Why is Q faster than R? Yeah, exactly. Well done, dear. Exactly that. This bond is longer. This bond is shorter. How do we know that? Well, bromine is bigger than chlorine. So the bond is longer in the bromine. If you have a longer bond, that means a weaker bond. And so therefore Q will be faster. Okay? Now, therefore, the answer is either A or B. Okay, Q is going to be the fastest because the CBr bond is weaker than the CCl bond because of bond length. You're quite right. Okay, so it's either A or B. Now, what's the type of mechanism for P? P is a tertiary, and tertiaries undergo SN1. So this is correct. This is wrong. Q is a primary and it undergoes SN2. There you go. So the answer must be A. Any questions there? That one was, I'd say, on a scale of 1 to 10, that's probably a 6. Any questions? Is anyone getting miserable and like thinking, oh my God, these are impossible? Is anyone? Or is it just me? Anyone at all? Okay, well, I can't see you at the moment. I'll come back to, whoops, there's, make this bigger. All right. I'm recording this, by the way. Maybe I don't know if that's a good thing or a bad thing. Right. Sorry about this. Just technical issues here. Okay, this one looks quite hard, doesn't it? Right, let's have a look. Where are you guys? Okay. Now there's the next one here. A sample of 2.3 grams of ethanol is mixed with an excess of aqueous acidified potassium dichromate. The reaction mixture is boiled under reflux for an hour. Oh, all right. The required organic product is then collected by distillation. The yield of the product is 60%. What mass of product is formed? All right, before we do any numbers, well, we start off with ethanol. All right, and we smash it up with potassium dichromate, Cr2O7. All right, where are we? Acidified. So there you go. And it says there's an excess, and it's boiled under reflux. So if I boil ethanol under reflux for an hour, what's the product going to be? Anyone? Well done, Banana. Banana, you're pretty good at this stuff. Well done. This is ethanoic acid. Okay, now let's find out the. Let's have a look. We've got 2.3 grams of ethanol, so the number of moles of ethanol is equal to 2.3 divided by the relative molecular mass of ethanol. Now, does anyone know what it is? Don't calculate it. Do you know what ethanol is? Anyone? If you do know, type it in. Some of these things are really useful knowing. Anyone know what ethanol is? No. I guess no one does. Ethanol is 46. You could work it out, obviously. All right. So I'm going to now find out the number of moles of ethanol, which is 2.3 divided by 46, and that's 0.005. So we get 0.005 moles of that, and we should get 0.05 moles of that. Moles and moles. But according to the question, we don't get 0.05 moles of ethanoic acid. We only get 60% of that. So we get 0.05 moles times 60%. That's the number of moles of ethanoic acid we get. And now I want to convert this number of moles to a mass of ethanoic acid. And we times by the relative molecular mass of ethanoic acid. And, because I've done a lot of chemistry in my life, I know what ethanoic acid is. It's 60. So this number here times 60 should give me the mass of ethanoic acid I get. So here we go. So times 0.6 is equal to that times 60. I get 1.8 grams. So the answer is C. Now, is anyone confused by that one? Because that's a hard one as well. That one's a tricky one, seriously. These are hard. I'm not joking. All right, I wish they weren't hard. Organic chemistry is hard. All right, so we're all good. I'm assuming if no one says anything, we're good. All right. So let's have a look. We're only at number 32, and we've already done half an hour. All right, but it doesn't matter. Okay, maybe there's an easy one coming. Let's have a look. All right, let's have a look at this one. The structure of tartaric acid is shown. All right, there it is. That's tartaric acid. That's what we put in ting. I think it's ting. You put tartaric acid in ting. All right, and you make it nice and sour. All right. So the structure of tartaric acid is shown. 4 moles of substance X react with 1 mole of tartaric acid. What could substance X be? Okay. Now, what reacts with these groups here? Okay. First of all, what are these groups? These groups are OH groups. 1, 2, 3, 4. Now, some of these OH groups are alcohol groups, and some of them are carboxylic acid groups. But what substance in the answers reacts with all OH groups? Anyone? What substance reacts with all OH groups? No, darling. Sodium carbonate will react with the acidic OH groups. That's a carboxylic acid, and that's a carboxylic acid. So 1 mole of tartaric acid will react with 2 moles of sodium carbonate. Okay? Is that right? Actually, I think it's going to be 1 mole. Yeah, because you've got 2 sodiums there. All right, so that's even wrong. I've done that wrong. All right, that will react with 1 mole of that. Sodium hydrogen carbonate, it will react with 2 moles because these guys only react with the CO2 groups, the acid groups. So does sodium hydroxide as well. That's only going to react with the acid group. But the thing that's going to react with the acid OHs and the alcohol OHs is sodium. So sodium is the answer. I hope that makes sense. All right. Again, that one wasn't too hard, to be honest with you. But you know what? You just got to learn these things, eh? All right. Now, I hope they don't get harder as you go along, but we shall see. All right. So let's make this one nice and big. Which compound gives an orange precipitate with 2,4-DMPH and a yellow precipitate with that? Right. Now, 2,4-DMPH, this stuff. Does anyone know what this sniffs out? What does this attest for? 2,4-DMPH. Anyone know? 2,4-DMPH. What will that sniff out? Anyone? Well, it's not the group it sniffs out, though, dear. It will react with aldehydes, but not just aldehydes. 2,4-DMPH sniffs out carbonyl groups. Carbonyl groups. Yes, aldehydes and ketones. Okay, so if you've got this group in the molecule, it will react with 2,4-DMPH, but it won't react with carboxylic acids, even though it looks like it's got the group, but they don't react with that. Okay, so they only react with pure, nice carbonyl groups like that. Ethanol doesn't have a carbonyl group. Methanol does. It's an aldehyde. Propanol does. It's an aldehyde. Propanone does as well. Okay, so the answer is B, C, or D. It's a bit of a pain. What does this react with? Yellow precipitate with alkaline I2. Alkaline I2 is known as the iodoform test. And this sniffs out this group. CH3CO. It sniffs out that group. So let's have a look at methanol. Does that have that group? That's methanol. And methanol does not have that group because it doesn't have my nice methyl on the left. What about propanol? 1, 2, 3. Well, does it have that group? No, it doesn't. Because there's that before you get to the CO. It's got to be a methyl, can't be an ethyl. So it's not methanol, it's not propanol. What about propanone? Let's have a look at propanone. This is propanone. There's propanone. Does this have this group? Yes, it does. Let's draw it. There's the methyl and there's the CO. It's the same as this group, even though there's a double bond there, but that doesn't matter. So the answer there is propanone. Any questions there? That one's not too hard, but again, you've got to know what iodoform test is, and also you've got to know what 2,4-DMPH does. Okay, let's have a look at the next one. Next one is 34. Okay, hopefully they're not getting harder. Like they used to, didn't they, in the old days? Right. A student suggests 2 uses of lithium aluminium hydrides. Okay, and there you go. There's one use and there's another use. Okay, now let's have a look. Does anyone know what what lithium aluminium hydride, what its job is? Does anyone know the job of lithium aluminium hydride? Anyone know? Yeah, it's a reducing agent, but it's quite a specific one. So lithium. Oh, where's my pen? Yeah, there it is. Lithium aluminium hydride, and you're quite right, dear, is a reducing agent. It's a reducing agent. But it's it is a strong one, but it's also a specific one. Specific reducing agent. In other words, it doesn't reduce everything. It only reduces some things. So in the top one, lithium aluminium hydride, actually, crazy but true, doesn't reduce double bonds. So it's not going to do reaction one. It's not its job to do double bonds. How would you reduce a double bond? Bonolo or anyone else? Lithium aluminium hydride can't do it. Okay? So we use something else to reduce a double bond. Oh, about that. Was it, dear? Was that a question? I don't know what's going on. Anyone know? How would you do reaction one? You can't use lithium aluminium hydride. You've got to use something else. Oh dear, the dogs are barking outside. I think they're murdering each other. Right, anyone know? No, darling. You don't use sodium hydroxide. Reducing agents add hydrogen, don't they? They add hydrogen. Okay, and if you want to reduce a double bond, what we use is hydrogen itself and nickel. That's how you reduce a double bond. All right. Now, hydrogen and nickel, this is a reducing agent. Okay. And it is not specific. This reduces everything pretty well. Okay. All right. So it does everything you want it to do. But lithium aluminium hydride only, this is what it does. It reduces carboxylic acids to primary alcohols. That's its job. Okay, so both reactions, no. Neither reaction, no. Reaction one, no. So the only thing it does is reaction two. It reduces carboxylic acids only. All right, so there you go. Let's have a look at number 35. That one was that hard? That one wasn't too hard, I don't think. But again, you had to know. You've got to know your stuff. It's horrible. Let's have a look at this one. Whoops, what am I doing? Everything's going wrong. Right, make that small. Okay. Compound. Oh, there's another calculation-y one. So, all right, we've got to deal with this. Compound X contains a single ester group. Compound X contains 27.6% by mass of oxygen. Which pair of products could be produced by the hydrolysis of X? Oh, my word. How on earth are we going to do that? All right. Now, oh gosh, what a horrible question, eh? So it's a single ester group. Now, what we could do, everyone, is we could just brute force it. So let's have a look at this one: butan, 1-ol, and ethanoic acid. So I'm going to draw this butanol, 1, 2, 3, 4. Oh my word. And then OH. And then I'm going to draw ethanoic acid. There's ethanoic acid. Okay. And when these two come together, they will form an ester. So let's draw the ester. So H2O comes off. Okay. And there's the ester. All right. Now, first of all, we've got to find out what mass of oxygen is in this. My word, what a horrible question. So first of all, let's find the mass of this thing, the relative molecular mass of this. Well, let's try and do it. 1, 2, 3, 4, 5, 6. So it's 6 times 12. That's for the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Plus 12 ones, plus 32 for the oxygens. So the mass of this, 6 times 12 is 72. It used to be. I hope it is now. So let's have a look at this. 72 plus 12 plus 32 is 116. I hope I'm getting this right. This is 116. But of this 116, 32 is oxygen. So 32 divided by 116 times 100. Let's have a look at this. 32 divided by 116 times 100, and I get 27.6. Yeah. So believe it or not, if I do this, I get 27.6% is oxygen. So believe it or not, thankfully, I'll tell you, the answer must be A. Now, is that understood, what I did there? Thank God the answer was A. All right, otherwise, we would have gone through them all, wouldn't we? But do we get that? Do we get why the answer is A there? 35A. Are we okay with that? That's a pretty horrible one because it looks awful. No one's answering, so I guess you're okay. All right. Now, this is going to be very strange when I record this. Well, I'm recording it when I post this because no one's saying anything. All right, here we go. Next one. All righty, let's have a look at this one. What is the least number of carbon atoms in a non-cyclic alkane molecule that has a chiral center? Oh, that's a mean one as well. Does anyone know the answer to this one? Well, anyone want to guess how we're going to do this? Is there a faster way? But no, darling, not really. Well, the last question. Not really, dear. Probably there is. And if the answer wasn't A, I would have showed you a few tricks we can use. All right. But not really, dear. Don't forget now, the exam lasts 1 hour and a quarter, doesn't it? So they've given us 15 minutes longer to do the nastier questions. Yeah, darling, yeah, you're right. Aish, yeah, you're right. It's hard. Getting an A in chemistry is hard. That's why you need it to be a doctor, eh? It's because it's hard. All right, what's the least number of carbon atoms in a non-cyclic alkane molecule that has a chiral center? Now, even though this looks quite an easy one, it's not really. First of all, what we have to know, for a molecule to be chiral, it has to have 4 different groups. Okay, and it says it's got to be an alkane. So it's got to be an alkane. All right, so let's do the alkane. All right, now let's have a look at what alkane is chiral. So it's got to, there's a carbon. This has to have 4 different groups around it. So first group must be an H. Okay, because I want the simplest alkane that's chiral. Second group, well, I can't have another H because now it's not chiral. So the second group must be a CH3. The third group can't be an H. It can't be a CH3. So it's going to have to be a CH2, H5. That's the third group. Now the fourth group can't be an H, can't be a CH3, can't be a C2H5. It must be a C3H7. So this molecule is a chiral alkane, all right, because it has 4 different groups. And there are the 4 groups. Now, to get the answer, we've got to count the number of carbons in it. Well, there's 3 there. There's 2 there. There's 1 there. And there's 1 in the middle there. So 3 plus 2 is 5. The answer is 7. Okay, so where are we? The answer is A, 36A. All right. Now that's a tricky one, isn't it? It really is. All right, 36A. Okay. So that's another tricky one, but not all. Yeah. All right. A molecule of a polymer contains the sequence below. A sequence shown. There it is. Oh, that looks a crazy one, doesn't it? Which monomer could produce this polymer by addition polymerization? Now, obviously, it's got to have chlorine in. So there's a group there. And there's one there. Okay. So what I'm going to do is I'm going to take my pencil or whatever. I'm going to draw a double bond there. And I'm going to get rid of everything on the left. Let's see if I can use this highlighter. Yeah, that looks good. I'm going to get rid of everything on the left and everything on the right. And that's the molecule. So the molecule is CHCl, double bond, CH2. So where have we got that? It can't be this one, because if it was this one, there would be chlorines on every carbon. That's not true. This one looks like the answer. This one is wrong for the same reason. This one is wrong because there's a methyl there. So the answer is 37B. Okay. I hope you get that one. If you don't, give me a shout. Look at the video when I post it later tonight. Eh? Right, next, let's have a look. Oops, daisy, wrong one. Let's have a look at 38. We're nearly there, guys. Don't worry. 38. Oh, there's a horrible. 39 is horrible, though. Right, paste that. And let's make this big. Okay, let's make this smaller. All right. Compound Y is heated with a mild oxidizing agent. One of the products of the reaction reacts with hydrogen cyanide, forming 2-hydroxybutane nitrile. What is compound Y? Oh my god. Right, now, here we go. Compound Y, okay, is heated with a mild oxidizing agent. Okay, one of the products of the reaction reacts with hydrogen cyanide. Now, on our course, hydrogen cyanide reacts with aldehydes and ketones to form these guys, these cyanohydrins, they're called. All right, that's what it does. On our course, that's what it is. So if we oxidize butanol, butan 1-ol, well, I don't know how mild we're going to oxidize it. We could get butanal, and then you would get butanoic acid. Okay? If you do butan 2-ol, you'll get butanone. If you do propanol, you'll get propanal, and then propanoic acid. And if you do propan 2-ol, you'll get propanone. Okay? Now, which one of these is going to end up with which one's going to end up with 4 carbons? Because which one of these starting materials, if we oxidize it, the number of carbons doesn't change, but the final product here, after we've reacted it with HCN, has 4 carbons. So how many carbons must there have been in the original compound Y if we end up with 4 carbons at the end? Anyone want to tell me? I know you're all tired, guys, but exactly, Bernard. There must have been 3. And this is what, well done, booklet. So this, A and B must be wrong. So it's propan 1-ol or propan 2-ol. Okay? So I'm going to guess, well, they're not going to go all the way. They're not going to use a primary alcohol because then you might not end up with a ketone. I'm going to say propan 2-ol. So let me do propan 2-ol. Propan 2-ol will give you this compound, which is propanone, this guy. And then let's add HCN to this. CN's going to go on there. And then the H is going to go on the other end, there. And what's this guy called? Well, this guy is called this is... this guy is not right, is it? This guy is called... Let's do the longest chain. This is propane nitrile. Okay, and this one is actually 2-hydroxy 2-methyl. So even though I thought they were looking at this one, it looks like they were looking at propanal. So let's do propanal. 1, 2, 3. There's that. H is there. Now this one is a tricky question for sure. Okay. Oh, Basadi's here. Hello, Basadi. Right. So there's propanal. And now let's add HCN to this. There's CN goes on that side. The H goes on that side. And now, yes, this thing here is 2-hydroxy butane nitrile. So I've got the answer in the end, but it took a while to get it. So the answer is 38C. That's a horrible one as well. All right. Now, as I've been saying a million times, guys, you can't. Oh God, this one looks mean. You can't do these the night before. You've got to really work at these. These are hard. They really are hard. Okay. This next one looks horrible as well. Let's have a look at this one. Look at that. Carotene. All right, there you go. Kerosene's a nice substance. It's very nice. All right. Anyone know what color carotene is? Have a guess? Lycopene and beta carotene. Carotene is, guys, you should know what color carotene is. It's orange because it's the thing that gives carrots their color. All right. So carotene and these two diagrams show the structures of lycopene and beta carotene. All right, and there they are. They're pretty complicated things, aren't they? When lycopene is converted into beta carotene, what is the gain or loss of hydrogen atoms per molecule? Oh my word! Okay, so how do we do this? Anyone want to give us a clue? How would you even start this question? What have you got to? Whoops! What have you got to calculate there? Anyone? Oh, yeah. Well, yeah, they look pretty similar, dear, but it's a bit easier than that. If they gain or lose hydrogen, what structure in one of the molecules will change? Anyone? What structure will change? Yeah, exactly. Well done, Sadi. It's the number of double bonds, isn't it? All right. So what we've got to do is calculate the difference in double bonds. All right. So let's do this. All right. This is how I would do it. Count them, and when you count them, do it with the pencil so you know you've done it properly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I've got 13 in lycopene, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I've lost two double bonds. One double bond, two double bonds. How many hydrogens does that mean? Since I've lost double bond, have I gained or lost hydrogens? Anyone can answer. Did I gain or lose hydrogens? I gained. Well done. Because if you gain hydrogen, double bonds become single bonds. And I've lost two double bonds. Each double bond, ladies and gentlemen, each double bond sucks in how many hydrogens? Each double bond sucks in how many? Oh, I think I've messed this up. Hold on, guys. Yeah, sorry, you've disappeared. Now, they've done two. All right. But, yes. Let's have a look. One, you know what? I thought, and I'm wrong here, which I'm glad, really. I thought there's two. So that means one, two, two hydrogens there, and two hydrogens there. So I thought the answer was four. Okay, everyone? Can you see where my answer comes from? You might not like my answer, but can you see what I was thinking? Now, what am I wrong? You can see what I was thinking. But you know what, dear? I'm wrong. I'm wrong. And I have no problem being wrong, but I am wrong. Apparently, the answer is C. Now, I don't know where I went wrong. Can anyone see where I went wrong? You try and help me, and I'll check I've got the right answer in the end. The answer, no, it says the answer is C. But does anyone tell me why? Oh, darling, I think you might be right there. Gosh, well done. Oh, gosh, you're cleverer than me, aren't you? Well done. So, can you see there's no change? Yeah, you can see. Well done. It's carbon. So, but anyway, how would you do this then? I've obviously done it wrong, haven't I? So, how would you do it, dear?
I have no idea.
Oh, guys, we got to dig it out, eh? At least my way was clever, even though it was wrong. All right. So what are we gonna do? Well, d- counting double bonds didn't help, did it? All right. So let's try and count hydrogens, eh? Do you agree with that, Basadi? You got to agree with that. Banana Basadi, whoever's listening, let me get rid of the. Oh gosh, what's going on? All right, I'm going to try and count. Oh, everything's gone wrong now. I'm going to try and count hydrogens in the top. Okay, now let's do the easy ones first. 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So far we've got 30 hydrogens, but that's not all. Now we've got to count out the loads of little ones. There's one there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 25. So I think there's 55 hydrogens there. Bloody hell, this is a mess, isn't it? And then let's do the bottom one. Now, according to the answer scheme, it should be 25. It's a lot of work, but I agree. Oh, Moses. Moses wants to come. You know what, Moses? You're welcome. But we started at 7, eh? Yeah, Basadi, darling, do you not think I am as well? Do you understand? Do you all understand what we're trying to do? We're going from the top one to the bottom one. Yes, but Ivana. The answer is C. Let me get rid of that. The answer is C. Yeah, the answer is C.
I have a question.
Yeah, go on.
Oh. Because that's a lot of work, honestly. No,
you don't think I know? Yeah, go on.
No, I have a suggestion.
Go for it.
You just look at the shape, because you see where the
there's a lot.
The ring is.
Yeah, you're right, darling.
You see where the ring is.
Yeah.
That one crosses, and then there's kind of like there's like a space. So I feel like that is looking indicator.
Yeah, I think you know what, dear. I think you're right. Oh dear, isn't that annoying? I think you're right, dear. I honestly think you're right. I think you're very clever there. I'm being a bit stupid, aren't I? All right, but I think Bonola's answer is wonderful. I really do, and I appreciate that. She's being cleverer than me. All right, so let's start again. But you know what? These sessions, that's what they're there for. All right. Gosh. Oh, why isn't this rubbing working? So well done, dear. I'm very proud of you. Because that shows pragmatism, which I obviously didn't show, didn't I? Okay. Because I thought it was going to be a simple case of counting the double bonds. All right. Now, Bonola's done this. All right. She's saying, well, there's a difference here. And there's a difference there. And everything else is the same, isn't it? Okay. So let's have a look at the difference in hydrogens in here. Right. Now, well, down the bottom here, all right, the only thing you're changing is, where are we? This one. Now, you've got one hydrogen there, all right. All I'm looking at is that bit of the ring, and one hydrogen there, okay? They are there, you just can't see them. All right, so there's 2 there, and there's plus 6 if you want to count these. Let's call it 8. Now here, in the same atoms where there's 2 here, there's none there, and there's 6 there. So there's 8 there as well. There's 8 there and there's 8 there. Now if we do the same on the other side, all right, let's count the hydrogens around here. There's a hydrogen there, there's 1, and that's it. Oh no, is there one there? There's one there as well. There's a hydrogen there. So there's 8 around there, and then when we make we have to count the same atoms. So when we do this, there's 6 there, plus now there's 2 there, so there's 8 there. So, Bonola, is that better for you? That's your technique. You taught me that, dear. I'm going to take that. I'm going to take that as mine. But do you get that, dear? It is way better, isn't it? Oh dear. I'm going to pretend it's mine though. You do know. Well done, though. All right. So everyone, well done. But Bonolo did that, and I didn't do that. All right, so well done, dear. But you know what? It shows you, doesn't it? An old dog can be taught new tricks. So well done, dear. All right, I'm very impressed. You're cleverer than me, you horrible girl. Right, now, oh my God, and let's have a look at the last one. The last one tonight, guys. You've done very well. You've been very, very patient. Jesus, well, this is the last one. The last one looks like a monster. All right, so, whoopsie daisy. So let's do this. But I have been humbled by Bonolo. So well done, dear. Seriously, I appreciate it. I like it when students outthink me. All right, now let's have a look. Now, which group shows the infrared spectrum of a compound that contains both that and that, a carbonyl and an OH? And they give you things at the bottom to help us with. All right, so I know a little bit of this, okay, because I've done millions of these in my life, I'm afraid. So I know I can do this quite quickly. If you've got an OH, yeah, it's around 3,000. Okay, whoops, what's going on there? Let's move that over there. OHs are around 3,000. So let's have a look down here. OH, yes, it says around 3,000. So anything with a, where are we? An OH is around 3,000. Now, I also know that OHs are broad. In other words, they're quite fat in this direction. Okay? So this one has an OH, and this one possibly has an OH as well, because they're both quite fat. Okay? The OH peak is what we call broads. In other words, it goes a long way either way like that. It's quite broad. So I'd say already the answer is B or D. The other one I know carbonyls, COs. COs ting at about 1250. Okay, so I look for about 1250. There's 11. Is it? Oh, no, it's 1700. Sorry, 1750. I'm confusing you. I should use the table, and I haven't. So let's see there you go. Down the bottom here, it's around 1700, 1750. So this one is a carbonyl one, and in this one there isn't one there, which is about here, about 1750 or so. So this one has the OH, which is this bit, and this bit is the carbonyl. So the answer there is B. All right. Now that one, yeah, that's just life, that one. You just got to read the thing. Benola, what's up, dear?
So when you're mentioning the peak for the OH, you said it's broad, but they didn't give the description in the.
They didn't, did
paper.
they? I agree with you. They didn't. That's something I know, dear. I must admit. Yeah.
So does that mean we have to memorize it, like
You know what?
the shape?
You know what, dear? I agree. Totally agree with you, because look at A. If you didn't know the OH is broads, if you didn't know that, A is a possible answer, because that looks around 1750, isn't it? Do you follow me? This one, so
Yeah.
it can't be C because there's no 1750. This is about 1500. 1750 is about there. It can't be C. This is about the same place. It can't be D. So the answer is either A or B. All right. This is 1750, about 1750, and this is about 1750. So you could have said, well, it's either A or B, and then you said, well, this is about 3000. And this is about 3,000. So the only way that you can know the answer is you must know the OH peak is broad. Now, Bonolo, what you said is, how are you expected to know that? And I think it's an excellent question, dear. I honestly don't know. I know the OH peak is broad because I've done a million of these. But how the hell do you know? Do you know what I mean? So look, it sounds unfair, and it is unfair, but we've just got to say to each other, in future, the OH peak is broad. Does that make sense? It's unfair, but does it make sense for today? Yeah, I know it sucks, doesn't it? The sun is coming now. It's not fair, but I can't see any other way out of it. Let's have a look. Does it say broad anywhere? It doesn't, does it? It doesn't say broad. Yeah? I know, but I'm with you. It's horrible. Right, now stay there a minute. I'm going to get the data booklet, which we don't use anymore, do we? Okay. But you stay there, and I'll show you something if I can find it. All right, now, oh, look at this. This is going to annoy you. Maybe it will, maybe it won't. Okay, let's get that. And I'm going to, oh, I don't think you can see anything, can you? All right, now, whoopsie daisy. All right, now let's push this up. Can you see? Yeah, well, it's only just gone. Now, look, this is the data booklet. Yeah? Can you see? What can you see? There. Banolo and Basadi and everyone else. This is the data booklet. There's gone. What's there? Everyone? Anyone see what I can see? You know what? Why do you pick on the weirdest thing, Basadi? Yeah, but look, there you go. The carboxylic, the OH group around 3000 is very broad. Okay, and you didn't know that, but now you know it. I'm afraid. But interestingly, a free alcohol group, free means it's not hydrogen bonded, is about 3500, and I don't think there was a peak around there. All right, so there you go. The OH is broad. What I remember is this. This is a typical IR. You got the broad OH, and you got the sharp, that one. This is about 3000, and it shows me an OH. This one is about 1750, and it shows me a CO. Knowing this, you can answer 90% of questions. Just knowing that, I promise you. Right, guys, we've been on for an hour and a quarter now, and I admire. I'm going to stop the video now. 1 second. Good night, everyone.